history, the S language was developed at Bell Laboratories, and it was really just available for people at the labs and a few universities. Some people broke away and formed a company that did a commercial version of S called S+. And that company had many names. It was MathSoft, it was Insightful, I believe, and that's the company that is now Tibco. Michael was with them all along. I left the labs in 1997 and started doing what I'm doing now. Michael arranged a lot of conferences for the company that did S+. As I say, its name kept changing. And several times Michael invited me to speak at his conferences. Well, as they say, what goes around comes around. It's more than 20 years later, and here I am inviting Michael to speak. Neil is new to the company, new meaning 5 years, so I don't know him as well, and I can't give any personal history with him. But with that, it's all yours, Michael and Neil.
Thanks, Naomi, for a great introduction. Yeah, my history with the S language, I first saw it back in the 80s, early version at the ANU, Australian National University in Canberra. I did my undergraduate in Sydney and master's degree in statistics in Sydney, and I came to NC State for a PhD, and I ran into the S language there. NC State Stat Department was one of the handful of organizations that got early versions of the S language, and so I started using it there. Initially on the VAC 780 and then on the Spark station, and been with the S language and R kind of ever since. And yeah, the Insightful got acquired by Tibco. Tibco's a pretty big software company. I think we're at about $1.5 billion in revenue. We have a lot of different products. Spotfire will show occasionally during this talk, but the talk is really about, and the other reason I got reconnected with Naomi, I saw this incredible moving presentation from your organization with Lee Wilkinson's daughter. I was brought to tears throughout the presentation. It was one of the most amazing presentations I've ever seen. Lee was a good friend of mine all the way from SysStat through SPSS. Dan Rope, his colleague and collaborator for many years, is now works directly for me at Tibco as head of our data science group. So yeah, it's what goes around comes around. Kind of thrilled to be connected back with. I see some folks in the audience that are chatting with already. So we're going to talk about visual analytics in time and space. Go through some quick review of some principles, and get into time and space, and kind of wrap it up. Yeah, just to kick it off, I guess Neil and I will be going back and forth on various things. We'll show some of our work in slides and briefly in demonstrations. But in terms of the the goal here of how we try and configure our visual analytics is to help perception of patterns, and accuracy and speed are both very important here. The bottom right-hand corner there, the human brain can process entire images that the eye sees for as little as 13 milliseconds. It's truly amazing what we can detect. And so being able to detect the geometry, the encoding of the values, being able to assemble groupings of graphic symbol elements to construct the patterns, and then assessment of relative magnitudes. Those are the things that we go through when we look at visuals and visual analytics, and they're all important. Accuracy and speed are all important. Just to sort of kick it off for fun, this is a customer of ours who uses our software for looking at electric power usage across the time of the week, is one of the things they do. And I just invite you to guess, what sorts of homes or businesses do you think are being represented in these visuals here? So the first one is a business. They're weekly, every day, you see a fairly consistent pattern there. And the next one is restaurants and nightclubs that have kick up in the evenings there, and single family homes that kind of putter along. Where there's broken meters, where you've got a downtown business that doesn't do business much on the weekend, and these potentially, though these turned out to be condos. But it's remarkable just what we can see from noisy data with the ability of our eyes and brain to kind of perceive these things. And so, the comparing lines, points, colors, and shapes, we're going to give you examples of how we use these different graphics elements. Humans are not great at estimating differences on graphs. So, they're okay at differences on lines, but not steep lines. We don't naturally order color hues. A limited number of hues can be discriminated. Red is emotional and can be perceived as larger. Larger regions appear darker, and there's Weber's law. The probability of detecting a difference in two lines is related to the ratio of the line lengths. Faint grid lines can help, and sorting by order of categorical variables is helpful. And then, Bill Cleveland's big contribution there, one of his big contributions for using the aspect ratio so that the average of slopes is 45 degrees is helpful. This notion of banking to 45 degrees. And so if you see, folks who write about, doing, that slide was about estimation. In terms of inference, the order of our perception abilities, position along a common scale is pretty accurate. Position along identical non-aligned scales is not too bad. Length and then angle and slope is kind of fourth, and then area, volume, and color are kind of below the line here. And so, this is a screenshot from one of Stephen Few's book, and you can see that we're pretty good when we're on a common scale. You can pretty much tell that one is less than this one. There a certain length of distance there, or higher to the or farther to the right, is greater 2D position, or once you start to get into width, size, and intensity, though, it's difficult. So this one you can tell that's wider, but not really by how much. Same with this and this, really. And so that's kind of just the background, and Neil's going to go through a little bit of some of those examples, using some data sets. And, most of the visuals you'll see in today's presentation are created in Spotfire. Neil, why don't you tell us a little bit about, some of these perception?
Sure, yeah. So we have this inference where we're able to perceive, we're looking at perceiving colors, shapes, lines, size, but our eyes are not as good at perceiving some spatial characteristics as they are as others. So one example is with length. So you can see here you have 3 pie charts, and they look like they're all about the same, but directly below those pie charts are a bar chart, and that bar chart is actually representing the data that is in the pie chart. So the length of those bars, it's very easy to see that the length of certain bars are longer than others, and there's greater values there, but we don't get that same perception with angles, angle and slope, which can be very difficult for us to perceive differences in. Next slide. Angle and slope with respect to line charts, when they're at 45 degrees, we have, this is where Michael was talking about with Cleveland, we have a better interpretation of the slope of these lines when we arrange our data in a 45-degree angle. So when that data is at the top and it's really spread out pretty wide, it's hard to see, for instance, those yellow outliers, how far they are from the exact cluster. They can be distorted and sent pretty wide out there. But when we arrange that in a 45-degree fashion with the overall data patterns in 45 degrees and our axes at our equal axes there, you can see those outliers in terms of their y-axis a little more clearly. Now, another perception is actually fixing your y-axis. So here's COVID-19 cases across different countries. So as Michael plays this, you're going to see on the left the cases per capita, and the cases per capita in the U.S., United States, United Kingdom. You can see that all relative to about 100 cases per 100,000. But when this moves on here to India, it's going to look much lower, and so here's India, and by adjusting the scale, we can actually see the India cases are still growing relatively high, relatively fast. But by fixing the scales, we're actually getting a comparison of that on a per capita. So inference can be aided by that.
Right. So the common scale, and then the ability to use the zoom slider to dig in where you need to, but being able to walk across the common scale and see the differences is pretty helpful. Keeping the patterns in your head, kind of thing.
Very useful in comparative analysis, comparative visual analysis.
Right.
So colors is another area of inference where, there's a lot of people may not understand the value of color here, but there's actually 4 key types of color guidance, color schemes that can be used: binary, diverging, sequential, and qualitative. So binary is when you might have two values, true or false, Democrat, Republican, just two different categories. Diverging is the same thing where you're going to have two categories, but there might be a numerical representation of it. How much of a county voted Democrat? How much of a county voted Republican? There's it's a continuous scale there. Now, if that scale goes from a minimum value to a maximum value, it doesn't go to two different extremes. It just goes in one direction. Then you might use the sequential, which is on the bottom right there, the sequential gradient scheme. And then if that's a categorical data that has no ordering, it's non-ordinal, you might use qualitative. So that can be like vanilla, chocolate, strawberry ice cream, or different colors themselves, or different states in the United States which have no ordering to them. That can be a qualitative thing. And so an example on the next slide is where these same data is used across 4 different charts, but with different color schemes. So in the top left, you're seeing a binary color scheme. This is honeybee colonies and how much honey they're yielding. So in the top left, you're seeing a binary theme where all of the green states are above average and all of the gold states are below average. So that's just taking the data that's continuous and dividing that into 2 different segments and making that binary. Now we can take that same theme, and in the bottom left in the diverging theme, we can see by the degree of how much greater or how much lower below average these honeybee yields are. So you can see like North Dakota and Louisiana, those are way over average, and then you can see states like Maine that are way below average. So you're getting that actual degree of continuity in there. In the bottom right, you're getting a sequential theme. So which states are producing the most overall, regardless of what the average is. And this is going in one direction with increasing color, increasing darkness towards higher values. And then on the top right, you're seeing just a categorical, no actual real ordering to this. You just have the East, West, Midwest, and North Central, East Central, different regions of the U.S. And that's just a qualitative thing. So not really ordering by the actual honey produced.
Right. And we spent, a lot of time on our colors, in our COVID live report. This is an online application that gets updated daily. It's been up for a couple of years. And we started off with the New York Times color schemes, and we kind of, morphed a little bit away from that to this, red to blue type scale, indicating, things going up versus things going down. Red is bad, sort of blue is good kind of thing. And we'll refer to this during the presentation somewhat, but we spent a lot of time on on that during that work that we did. So when you kind of look into different states, you'll see, or different countries, you'll see how the different color schemes play out. But I think just to build upon what, and we'll come back to that COVID application. It's a bit of a signature application in exercising some of the principles that we're covering today. The other thing is that, we do a lot, not just reporting, but with interactive visual analytics. And so, using Ben Schneiderman's mantra from the, I think it was IEEE publication. It's got a lot of citations. 3 levels of understanding: an overview, followed by a filter or mark or zoom into an area of interest, and then getting details on demand. That idea of being able to quickly get to the important information while your brain is still active around the sequence, is important. So this is a New York City demographics, and I'm looking to see where I might want to put a new store there in that yellow dot. I might zoom in and find around that location, who lives there. There might be, you see the details on demand there in the tooltip around who's living there. And then you might, zoom in and see what sort of attributes those folks who live nearby there have in terms of income, miles to the new store, things like that. So that interactive, call it interactive brush linking, or interactive visualization is another aspect of that. So that's just basically the setup and principles that we're going to cover in today's talk, and we're going to refer back to those. But let's start off and get into the first section of the talk, which is on time-based visuals we'll get into some basic principles, time varying displays, event stream analytics and applications. We'll do the same thing for, spatial data after time. So some of the basic principles here, if you're looking at time series data, what sort of granularity should you look at it on? Hours, minutes, seconds. You can use a parallelogram to figure out, the granularity in the data and the what sort of aggregation level you might want to apply. So the aggregation might be mean, median, time weighted average, whatever. And where possible, being able to line up the different data channels is to that granularity is useful. But you see, and this is a data set from an accelerometer. So this is, and someone was wearing it on their belt. And you can see the X axis, the X dimension, it's a three-dimensional data coming off, is in the top row. The Y dimension is in the middle row, and the Z dimension is in the bottom row. You're getting three coordinates from each time you take a reading. And this was, giving us lots and lots of readings, and we're trying to figure out how to summarize them for visual analysis. And so as the person is jogging in the first column, or walking in the second column, or standing in the third column, we're starting to collect data from the accelerometer. And you can see the autocorrelation for jogging is not, well, the correlation as a function of lag is not very high when someone's jogging along. When someone is walking, it gets to be a little bit more autocorrelated. When they're standing, it's very autocorrelated. So you can use that as a way to aggregate your data. So in this case, we've got the raw data coming off of the accelerometer, and now we're summarizing it. And you see in the top right, we're keeping track of the number of events that are coming through, and then the aggregation that we did based on the granularity we derived from the parallelograms, and then the number of predictions. So we're able to take the XYZ data at each time point, and we're able to predict whether someone is jogging in blue or walking in red or standing in green. We're able to do that prediction, and we're able to put that little machine learning model into the accelerometer, and we did this as a demo. Someone was walking around or jogging around on stage, and we're able to predict what their movement is. Useful in FedEx is a big customer, understanding how their package gets delivered for sensitive materials. But that's an example of time series data. Now, Neil, you want to talk a little bit about how we look at time series data visually and summarize that?
Yeah, no, and this is a great example of also with the estimation. So this is time series data that's looking at COVID cases again across the US. And you're seeing this as a pretty noisy curve of information. There's different reporting cadences from different agencies. There's weekly patterns, there's daily patterns, there's monthly patterns, all of that's kind of mixed in there. So on the next slide, we'll actually see a better estimation of this, which is 7-day moving average. The 7-day moving average can really aid your eye in perceiving that epidemic curve. But at that top peak, you're seeing a little drop up. You're seeing two little drops there. Michael can point out on the Thanksgiving and Christmas time. Around Thanksgiving and Christmas, you're seeing two drops in reporting. And that is because this 7-day moving average is overfit to the data. And it's also got a little bit of a lag. A 7-day moving average will have a 3.5-day lag in the reporting. So what we've used is a Friedman super smoother, and the Friedman super smoother is a local bivariate regression analysis that will actually make predictions at every point. And this actually is doing a better job at estimating that curve. It doesn't have that 3.5-day lag, and it sees right through the noisy data in that Thanksgiving and Christmas period, and giving us a really good epidemic curve in that white curve you're seeing there.
Right. And you can see that in the, if you go online and take a look around on here, you'll see how we extensively use the super smoother in all these different visuals throughout here. It also allows us to get an estimate of velocity by looking at the first derivative of the fitted curve. But you'll see throughout, this application where we're using we're smoothing the epidemic curve essentially to look at those data. So yeah, and the US county stuff, has really been going up and down quite a lot lately. Okay, so time varying displays. Neil, do you want to take us through some of the basics of time varying displays?
Sure. So the most common time varying display you'll see is a line chart. And this is really great for continuous timelines. This is good for showing historical trends with the time, magnitude change between different categories. and also like forecasted trends. So this is the most common type of line chart. It gives you a historical trend. It gives you where you can forecast in the future, and that relative comparison. Now, the next one is, this is actually a velocity chart. So if we can take the first derivative of the actual line that we're using, the actual trend, then we can actually see the rate at which that's changing. So we use this with our COVID analysis, not just to see what that super smoother was doing, but below it, we can see what rate was that actually changing, what speed were cases growing, or were they dropping. And this can be good for, especially good for exponential data, or growth rates that are changing very quickly. And this can really help your interpretation of that. And then next you have a bump chart, and the bump chart is similar to a line chart, but this is not really good for analyzing different magnitudes. Instead, this is looking at measuring relative rank, and it can really simplify the view of many series. You don't have a lot of overlapping lines. You're really just looking at the rank of these over time, and you can quickly see which ones are rising relative to other categories in your data. Next from this is the Gantt chart, and this is good for discrete timelines. It's often used in product management. It shows duration of tasks and plans, finding overlaps and dependencies in your data, and measuring the progress of your tasks with respect to your overall timeline. The next chart is a candlestick chart. Michael, do you want to talk a little bit about the candlestick?
Oh, sure. I think everyone's probably familiar with this, but it's basically the financial data with price movements, typically on a daily schedule. And so the body of the box is typically the price range between open and close. The whiskers, the high and low value. And the color is whether it's trending up or down. Up is bullish in blue, and bearish in red. So there's quite a lot of information gets delivered with a candlestick chart for stock tickers. And then animations. Wonder if we have this is good for storytelling. Hats off to Hans Rosling for the Gapminder TED Talk. And we've been implementing this, wherever it makes sense. And, for the COVID application, we added a visualization, in the early days of the vaccination. Let's see what happens here. There we go. With people vaccinated per 100 on the y-axis, and new cases per 100,000 on the x-axis. I guess this one is for US states, and you can see, we started in January of 2021, and now we're getting into May, and you can see the spread on the y-axis in vaccination rates on the different states. Sort of Vermont at the top, Mississippi at the bottom, and you can see what happened when Delta came along. All the states along the bottom with low vaccination rates had their case count jump up. With the Delta variant, and then sort of came back to the pack there. We're now in November, and with Omicron started, and you can see there was all of the states pretty much moved across with Omicron. Didn't matter on the vaccination rate on the y-axis. Although the states that had high vaccination rates seemed to recover faster. I guess this went up until January. If you go to the application and you kind of take a look into the vaccination page.
Just right. Yeah.
Let's see. I'll do the global one, seeing as we just did the US one. You'll see the cases per 100,000 and the vaccination rate per 100, and you can pop out this animation here. You have some controls over here on speed. We can jack up the speed of the playback. And if I go, I just highlight the countries here, or I hit the play button. Again, you'll see that same sequence. In this case, Israel got off to a quick start with vaccinations on the y-axis, and some of the other countries kind of came along a little bit later. I have to grab the markers again, but you can see when we got to the middle of the year, again, you can change the x-axis, y-axis. The color is by case velocity. The size is by total vaccinations. You can change those. But you can see, different countries going up there, and a big spread on the y-axis in terms of vaccination rate. And then as we get, we had to change the scale when Omicron came out so that we could fit everybody in. But you can see when we got into the Omicron period, a lot of the countries moved out to the right here in December and into January. So again, hats off to Hans Rosling for the great visual analysis, and we've been as we've been creating these mods, we call them extending the visual palette. We've been building some of these out to use in interactive visual analytics. Now, when time-varying displays, being able to calculate, events on the event stream, doing things like, moving averages or calculating slopes directly on the event stream. We have a product that does that. And then you can use that to figure out, if something's trending in the wrong direction, you might want to make an intervention. So you can see that on the top right-hand corner. And this is a bigger display showing, these are actually oil wells in Houston, and you can see the pressure and current coming off of the equipment. And you can see that you might want to set an alert here on the pressure in the top left there, or motor temperature, motor current, or intake pressure. And you can see how those you can move around on with real-time data coming off the equipment. So getting into applications of time series data, being able to put a bounding box around moving equipment and do a deep sort calculation that handles occlusion when one object comes in front of the other, and being able to measure things like the vehicles count going by, the speed, the average by class, and so on. So this is a demonstration of a video feed from a cafe in Sydney near the Harbour Bridge, a publicly available video feed that we analysed to put a hold on bounding box around the cars and calculate their speed, figure out what kind of car they were, look at the distribution of different types of vehicles over time, and understand their movement patterns. And other examples of time-based data that we get into quite a bit. One is in the area of predictive maintenance, where we're doing a reliability analysis, looking at, say, failure versus time in service. And if there's a particular cost associated with doing a maintenance versus the cost of doing having an unplanned downtime, being able to trade off those costs and then look at what is the optimal maintenance interval, this vertical line here, that trades off the probability of a unplanned downtime in this red curve, multiplied by the cost of an unplanned downtime. And then the green curve is the cost of maintenance. So you don't want to maintain your equipment too often, or your maintenance cost is high on the green curve, but you don't want to let it run too long, or your cost on the red curve, the unplanned cost, goes up. And in the middle there is a sweet spot. And you're able to look at this, this Weibull two-parameter exponential analysis to figure out what is the cumulative probability of failure versus time, and use that to basically, once you get that cumulative probability, you multiply it by the cost of an unplanned failure, and you get that red curve. And then this green curve is very simple. It's just the cost of maintenance, depending on how many times you maintain it. So the calculations are pretty simple on this, but it's very a high value application for people who have got equipment, being able to figure out that maintenance interval and plug in their cost of a maintenance event and the cost of an unplanned failure, and then adjust those curves based on the distribution function that you get for the cumulative probability of failure as a function of time from that reliability analysis. And there's that CDF up there in the top right-hand corner that you multiply by the cost of the unplanned event, and you can put various thresholds around that and understand that in more detail. Now, that predictive maintenance piece is one side of the coin when it comes to equipment, and the other side is anomaly detection, is being able to continuously monitor the equipment, like in the oil example I gave earlier, where you're getting data off the equipment and you're able to look at it quickly. Now, with respect to anomaly detection, this gets interesting when you're in two dimensions. In one dimension, you can just put like control charts around things, and you can see when things drift off outside the control charts. But, you might have, say, your Y2 measurement, these red points might be pretty much within range. And in your Y1 measurement, these red points might be pretty much in range. But when you look at Y2 versus Y1, then you can see you've got, some anomalous points here, and you want to be able to understand, are they related to a certain tester or a certain part of the process? So that, when outliers are only appearing in multiple dimensions, you have to come up with some other way of finding them than just your standard, statistical process control. So this is an important time-based visual analysis, because you want to look at multivariate data on a time scale. Each one of these time points, you're getting data on one of these 9 measurements, and you're trying to figure out, when did my multivariate process go out of control? So, one thing you're able to do is to fit like an autoencoder or a long short-term memory type neural net model and figure out when the reconstruction error of that model goes above a certain threshold. And so that, you can find your incidents where you've got a, sequence of data points that have gone outside of the control, the multivariate control point. And I can now see what variables here, the pressure or efficiency, waste gas, and so on, what ones of those variables are the root cause analysis for understanding why that nine-dimensional process went out of control. You've got a bit of a root cause on it. Now, once you've got, you build up a collection of anomalies or incidents, you then might want to understand, what are the factors that affect, what are the root cause factors that explain the anomalies? So when we collect up a bunch of the anomalies, we can then look at understanding them and clustering them into different groups. So in this case, we've figured out there's like about 4 clusters, looks like, from the elbow plot. And now we build the clusters, and we can see now that I've got 4 clusters. Cluster 4 is the biggest one. Cluster 2 is a pretty big one. You can see it's dominated here. This network visualization is showing that there's a particular sensor or a particular one of those 9 measurements that is really responsible for those 2 clusters, the blue and the green one. And then the pink and the purple ones have got a number of different contributions from the different variables. These are the variables that we're measuring at every time point. And we try and understand which ones of those X variables are, variables are responsible for the anomaly or the incident. And we found in this case, there's 4 different clusters that we've been able to represent on this network visual, with the width of the line here being proportional to the amount of importance of the variable that is associated with that particular cluster. So you can see pretty thick lines for cluster 1 and 3 with respect to these 2 differential pressure readings. The blue cluster is a differential pressure reading number 6 is a dominant root cause variable. And the green variable here, differential pressure number 1 sensor, these are all sensors pretty much, is responsible in large part for this cluster number 3. And then cluster 2 and 4 have got different contributions from all of the sensors. But the network visualization is useful for being able to kind of display the interactions and contributions, in this case, of the different variables to the set of anomalies. Okay, so that's a bit of a whirlwind tour of some examples in the time part of the talk. And Neil is going to give a lot of the space time of the talk. So Neil, actually, do you want to kick this off? And I think you're going to give most of this part, right?
Yeah. Do you want me to present from my side, or? Yeah,
why don't you do that? So while Neil is setting up, any questions on the time section of the talk? I mean, we'll have time for questions at the end as well, but if there's any questions, or I can just jump into chat now and see if there's questions there. And yes, there was. The ayes have it. Ben Schneiderman's paper from 1996, indeed. So I've got a pretty deep collaboration with Ben. That's his human-computer interaction lab at University of Maryland was where Spotfire was invented. And so Ben and I go back a long way. He's actually doing keynote this year. He's got a new book, Human-Centered AI, and he's doing one of the keynotes at our analytics conference. But yeah, Neil, let's take it away on the space part of the presentation.
Yeah. So first was time. Now we'll talk about space and some different spatial principles. So basic principles with space. So first of all, the benefits of spatial data. Spatial data, such as maps, you're going to have improved interpretability of size, shape, boundaries, density, proximity, context, especially that context piece. You're really getting a lot of visual information with a spatial plot. Now, spatial plots are typically comprised of 3 different types of objects: points, lines, and polygons. And with these, you can make any type of spatial representation or graphic, such as this is a floor plan of the San Francisco airport, and this is actually done in a shapefile with lines and polygons to represent different locations within that floor plan. Now, the most common type of map is a geographical map, and there's different types of geographical maps. There's topographic, climatic, there's economic maps. They may be used to represent where land and water is, features such as roads, cities, elevations. We're all familiar with geographical maps. Now, maps geographical maps do have projections, how those points and those objects, those lines and polygons, how they're going to be represented across the surface of the Earth is a map projection. And that's something that should be in your data file if you're doing data visualization, understanding which projection you're using for your spatial objects. There's also different coordinate reference systems, and that can be a different way to represent different points along the different projections in your geospatial graphics. Now, another type of geospatial graphic is a choropleth, and a choropleth is really good at measuring variables across a geographic area. It can create distortions if it's not visualized correctly, it's not normalized correctly, but it does prevent the overlap of data like you would get in a bubble map or a marker map, point map. So this is a choropleth with each individual boundary representing a measure of a certain variable. Next on that is a cartogram. And a cartogram is very similar to a choropleth, but the cartogram has the benefit of removing the spatial bias from boundaries. So a cartogram will actually distort the shape and the size of the object based off of the measure that you're using. So this is actually, again, COVID-19 data. This is in the early part of the pandemic, and we're seeing which states were having, Wyoming over there in the Midwest, the West over there, Wyoming had not very many cases and it's kind of coming crunched in, whereas Texas, California, Florida are kind of ballooning out as the cartogram expands those to represent the COVID-19 case data. The floor plan and building map, this is showing different features of buildings and structures, indicates resources and accessibility. And these may be in arbitrary direction. Most geographical maps will have north pointing at the top of your map, but these could be in any different orientation and have interactive polygons that you can use in data visualization tools such as Spotfire. Similar to the floor plan or what we've done similar to a floor plan is a tree map. And Michael, did you want to talk about the tree map, or do you want me to continue here?
You can just keep going, Neil. I was answering questions.
Sure. Yeah, I'll just talk about the tree map. So no problem. So here's something we've done with Dartmouth University to understand which of their rooms, which of their buildings were highly visited by different students. And we're able to actually visualize that in this tree map, which has darker colors for high concentrations of students and larger sizes for the larger room. So we can see we have a large room with a high concentration of students. Here we have some small rooms that are not being visited at all. And here we have some large rooms that aren't being visited as much, but kind of medium visitation. And this was used for the janitorial services so that they could actually do room cleaning during COVID-19 pandemic and to actually keep the facilities safe and relatively accessible to the students. So the tree map is going to color, and this is actually a Ben Schneiderman invention, is the tree map. So Ben Schneiderman, someone we've been talking about today. And this is colored in size to represent different variables, and it's a very efficient use of the visual real estate. So the spatial aspect of this tree map is actually very efficiently laid out. Next, we have a heat map, and the heat map can be used to represent space and time. It's going to be actually representing the space of your data. So where are you having clusters of your data? This is looking at COVID-19 hospital admissions by day and hour in a certain hospital in Jacksonville, Florida. And this is a fixed cell size also make efficient use of the space. So we can see these fixed cell sizes all throughout the plot. But this is emphasizing where in our actual data set there are clusters of data, and it gives that nice normalized view of the spatial representation. The heat map is good for multivariate space. So this is showing a network plot that's similar to the autoencoder that Michael showed, but there's also a heat map on the left, which is showing variable correlations. So variations of color emphasize correlations in the data, with purple being highly correlated variables and blue being less correlated variables. So we can see with this heat map how our variables are related to each other. So this is another use of a heat map. In the network map, it shows relationships. We've talked about this a couple of times, the network map, but how it relates spatially is it shows relationships between entities and maps these complex connections. So when you have a multivariate space or a high parameter subspace that you want to visualize and understand better, the network map can help you keep track of these multiple dimensions. So this is actually looking at opioid prescription data, and this is a analysis where we were analyzing opioid trafficking around the US, and we have this network of sellers and buyers, with each cluster representing where a seller is and each point recognizing a buyer. So we can see which buyers are going to multiple sellers, which buyers are going to the same seller, which buyers are maybe going between sellers. Now, next is spatial operations, and spatial operations are what we can do on our data, our spatial data, to get more value out of that. So there's many different types of spatial operations. There's search, location analysis, terrain analysis, there's measurement. We're going to cover some of these, like the Voronoi. Let's see, where's my mouse? The Voronoi, the corridor, buffer. These are all useful spatial operations. The first one we're going to talk about is proximity, and in spatial proximity, we can see here the location of this store in the New York City area, and we want to find demographics that are near this store. So what we have is an ability to actually do a geospatial calculation to filter out data that is not near the store. Let me play this. We can hover over this and we can see, oh, these are the different demographics for different census districts. I can select some data, and this is going to select the nearest data to that store. It's going to be the proximity analysis. And we also have a spatial buffers. Spatial buffers can be used here. This is on horizontal wells that were being drilled in the Texas region. These horizontal wells, they have certain drainage. You don't want to space wells too close to each other because you might hit another well. And so this actual calculation goes and does a 2D matrix of the well locations, and by adjusting the slider, we can adjust the distance cutoff, and that creates a buffer around the actual well location, and we can find then the safe zone for drilling. Next up is this is feature extraction or point extraction. As I select, this is a river network in Ireland or Scotland, sorry, in Scotland, the different rivers around a certain catchment area. And as I select the river polyline, I can extract vertices and interpolate points at every 100 feet. So this is a way that I can then get continuous analysis. If you're familiar with spatial data, such as points, lines, and polygons and shape files, you'll know that one record might be a polyline, and with that one line, you can't actually do a continuous analysis. So by converting that line into points, we can then do things such as a spatial join. And the spatial join here, we have different red points along the river catchments, and that's river pathways, and those red points are the pollutant measuring stations. So where different pollutants are coming in, but how do we know how those pollutants are actually spreading across the river network? We can do a spatial join to join all those individual points that we extracted from the river, join them to the nearest pollutant station. And we can do that by doing a spatial join. And it's a multi-layer approach here, where we have a layer of data from the pollutant stations and a layer of data from the rivers. That's those dark black points. And as we adjust the spatial cutoff, we can see, okay, here's how the pollutants are spreading across the river. And that allows us to actually interpolate the data across the river. So you can see these points, these circles that represent the pollutant stations, measuring stations, and how that's actually being spread continuously across the river area. Spatial patterns. Spatial patterns are used, one great way spatial patterns are used is in generalization. Generalization is when you have a lot of different points and you want to generalize that to a layer that you can get a comprehensive view very easily. You can generalize that view. So rather than looking at every individual granular point, we have a grid bin here, and this grid is actually representing different insurance claims in the Florida region and different types of claims, which aren't labeled here, but you can see the different categories of the most common claims that are being done around this Orlando and Tampa Melbourne area of Florida. So that's a grid bin generalization. Another common type of generalization is the hex bin generalization. And this has an advantage of using, rather than using square bins, which have a bias in making your eyes go vertical or horizontal, hex bins actually allow you to look at angles better as well. And this polygon tessellation, in terms of packing, the hexagon is 13% more efficient in covering the plane than the squares. So you're actually getting more coverage here than you are in a typical grid bin. And then hexagons are, again, less biased for displaying densities than other tessellations. The density generalization can be used to take a lot of clusters of different points and then generalize that to different isopletes here. So here you're seeing isopletes of a cluster of points in the Northeast, and then you're getting different areas around Chicago, Chicago over here, and Detroit. So the density generalization can be good to take source points and build a contour here, and major contours, minor contours, and actually color that with a heat map.
So Neil, I think maybe I'll bring it home from here.
Yeah, sure.
But you know, I just finished answering all those questions, and we've just got a little bit left to cover. So yeah, the heat map generalization, and one of the questions I was just answering from Cameron, you know, what do I like about having different things at my fingertips? You know, with respect to both time and space, but you'll see in this this video that we've got county level case counts across the US, and you can see that I'm just made an arbitrary marking with my mouse on that region, and you can see that what's happened, you know, in response to that, as I've calculated, you know, at the hotspot analysis, essentially, where we've got lat long centroid of the counties, we get the Z value, and then we do a low S smooth of that Z value, and then we color by the low S of Z evaluated at a fine grid. And that all happened by just making a marking. So that's kind of what I was talking about, Cameron, in the chat, about what I do like about, you know, having at your fingertips the ability to do calculations, you know, on the visual analytic. From menus is fine, but doing from arbitrary marking is something that I really do enjoy about using, you know, using the our TIBCO products. And I guess this was what I should have gone to this slide and shown it there. The other slide was actually, you saw how long it took to the little bit of a lag there to do all that calculation. And this one's got it all sped up there. So to bring it home with geoanalytics, you know, geospatial analytics, one example, Voronoi tessellation, you know, all points inside of each of these polygons are closer to this centroid than they are to any other point. So that's useful for generalizing regions in points. So for example, in this case, we've got geology data in the energy sector, and we've got well data. And so we're putting a Voronoi tessellation so that the geology samples are grouped in a way that can be informative when it comes to predicting the production of the well. So when you lay the well production over the top of that, you can see which of the geology samples you might want to use for predicting production. Here's another example of the Voronoi tessellation with this time with people living in certain region, and you know what clinics are closest to what people, and you know when you have multiple, you want to add clinics, for example, where would you put them to make it cover the population efficiently? A trade area analysis is when you know you've got a certain point and you want to find what is the you know, say a 3-mile drive time from that point, taking into account, you know, when you've got bridges or roads, you know, all of that more practically relevant than, you know, as the crow flies. So on that COVID application, if you want to play around with that section of it, you'll see you can basically go and find a region of the US. You can click on it, copy the map coordinates, paste it into this little box here, pick your driving distance, and then click the button. And you'll get, you know, in a certain, I guess, 5.7 miles from wherever that point was clicked there in Seattle, you'll get the driving distance of 5.7 miles, and you'll see where all the clinics are, you know, in that region, you know, taking into account bridges and roads and everything like that. And then finally, to bring it home, applications. We've been doing quite a bit with, you know, when there's high dimensional data, to do a principal component analysis and reduce the dimensionality, in this case, to 6 dimensions. And you can see on a self-organizing map the relative weights of those different 6 dimensions. So you're organized. So when you look, in this case, in this bottom left-hand corner where you've got high weights on all of the individual principal components, and then you look at that 1 pixel, you expand it out, you can start to elucidate structure in the geology. So we use this for analyzing seismic data in the energy sector, where there's lots and lots of dimensions of, seismic data. You bounce sound waves off the rock and you get back a lot of different columns of data. So this is a way to summarize that. And I guess there's a little bit more here on how that works. I'm kind of running out of time, so I might skip this one. But and the other final example here on semiconductor wafer maps, we do a lot of spatial analysis here. And semiconductors, these parametric wafer maps map a single value at each location on the wafer. This one is a smooth representation to look at different patterns, spatial patterns. And then bin maps map multiple test values at each location die. And an overlay analysis, a lot of the chips that are used for memory in your phone have got like 128 layers of that you've got to line up. And this is done at nanometer scale, which, there's, I think a human hair is like 100,000 nanometers, 10,000, I think 10,000 times, human hair is 10,000 times as big as a point on a high-tech manufacturing wafer map. And so we do a lot with representing different data all across the wafer map, different variables, composite bin maps, and getting yield and looking at patterns. And this is actually the latest work I've been doing with Ben on his human-centered AI project, where you have a human and a machine learning model going back and forth. So I run this video. We start off with the human finding the pattern on the wafer map that's of interest, like that one there. And then going and finding wafers that are similar patterns to that, creating a pattern. We're calling this one a scratch. You add that new pattern to one of your existing patterns. And then you basically go grab the pattern. In this case is a ring pattern. And I'm going to go fit a model to be able to predict that ring pattern. And now once I have that model, I can put that on the event stream. And as new wafers are coming off the manufacturing process, I can see, what pattern are they? Are they an edge ring pattern or a heart or a crab or whatever? And these patterns relate to the yield of the process. And so it's a highly valuable thing to be able to figure out what are the factors that affect you getting an edge ring. When you get an edge ring, the chips on the outside of the wafer here have to get thrown away. They don't work. And so this is it's important to be able to identify those sort of patterns. And then I'm just going to wrap it up today with a quick application from F1 Racing. The F1 Racing season starting next weekend. We have a partnership with the Mercedes F1 team. We do a lot of their visual analytics and data analysis, setting up the car for the weekend with simulations and digital twins and understanding what are the factors that affect lap time. And in fact, if we were at an event, we could show you this. You can jump in this car, at the TIPCO booth when we get back to doing live events, and you can see you can drive the car around, and we're predicting the speed and the current lap. What's the predicted time for the current lap as you drive around the track? So this one really is combining time series data with spatial data, because you're driving around the track, and we're predicting your lap time from the time sequence of your data. So thanks for watching. A bit of a whirlwind tour, but I hope it was helpful. Some of the work we're doing with data from time and space, and some of the visual analytics that we're working on at TIPCO. Our analytics forum this year is June 13th to 15th. It's a virtual event. It's free. There'll be a lot of people talking about visual analytics and inbuilt data science, machine learning. The products that we have Python and R and interactive visual analytics all kind of joined together. So I would be happy to host you there, and otherwise let's open it up for questions.
Thank you so much. Put your questions in the chat and Michael or Neil will answer them. There's one in the chat now, Michael.
Okay, does Spotify support global maps in something other than what appears to be Mercator's, as in projection that doesn't make global north look much bigger than it actually is? Yeah, I think there are different formats that Neil alluded to there. We do.
We have like over 100 that I think actually ship with Spotfire, 100 different projections that you can choose, and then you can actually use a custom projection as well.
Yeah, and when you calculate distances on the map, we do take into account the curvature of the Earth. We acquired a geoanalytics mapping company, Maporama, French company, probably, I don't know, 6 or 8, maybe longer, 8 years ago, and that became the map chart inside of Spotfire. They also have we now have a product that does geoanalytics, that supports retail, mainly the retail industry, for doing drive times and deliveries and things like that. But it's the map chart in Spotfire is pretty detailed and comprehensive.
There's another question. Can the user input their own boundary file, or must the data match up with the boundaries already available in the package? You can bring in your own shape files, your own boundaries that will actually use whatever projection file your shapefile is created in. And that's automatically aligned up. So it's not just the projection files or boundaries that are available in Spotfire. You can bring in your own.
Yeah, there's a couple of slides we left out of today's presentation in the interest of time that talks about how you can stack up the different layers, whether you've got a marker layer or a feature layer or a shape file. You can kind of layer those on top of each other and do calculations between the different layers. And that's Linda Pickle. I remember, working with Linda and Dan Carr and doing quite a lot of geospatial analytics back in the day. And I was moved to see you and Dan at the Tribute to Lee presentation, I guess a couple of months ago.
There were some questions that you answered in the chat before that might be useful for everybody to hear.
Sure. I think I was mainly talking with Cameron, and it was great that Cameron gave the citation, the eyes have it, Ben's IEEE paper from '96. And yeah, I think what I was saying to Cameron was, Cameron asked about, what are your thoughts on what calculations you want to do inside of your visual analytics tool versus, doing them outside and bringing them in. There's value in both of those approaches. And I think I was pointing out to Cameron that I like having, the visuals inside the application, especially when you can make an arbitrary marking on a map or whatever. And Neil showed some of that, but if we, let's see if I go back to my overview here, and if I go into, what's a good example of doing that, Neil, I guess? I
mean, the heat map is a good one.
Doing a heat map on the US counties is that, I think, the one that you showed, right?
Yeah.
So yeah,
if you go off of marking,
that's a good one, because you can, if you click on the marking part and you can kind of draw an arbitrary region there. I guess this is today, 14th of March, a couple of days ago. Being able to get that hotspot analysis. Basically what's happening behind the scenes is there's an R data function, which is reading in those county files and doing that analysis on the centroid of each county and getting the value of the cases and smoothing that and, putting that micro kind of contour plot back on top of it. And so being able to do that, an arbitrary marking on any graph and run an R script or a Python script. R's got really good spatial analytics libraries like, RGDAL and so on, that you can, return a well-known binary object, which just renders right on the map chart. Python we use more for, data prep and machine learning, but having the ability to fire off any R script or any Python script from an arbitrary marking on a visual, that's the unique thing about Spotfire that, has excited me from the beginning, and that we've kind of been building on top of these last many years with combinations of R and Python with interactive visual analytics. And you can see down below there, we got the, for those individual counties, we got the, the velocities, and then down below that, we got the past 7-day case counts. Things are settling down, but go ahead.
I like the middle one, the second one, because right now many of us are aware that COVID cases are down. The Omicron wave has kind of subsiding, cases are down, but are they continuing to go down? How fast are they continuing to go down? That's what we're seeing, is that they're still dropping at a rapid rate. So it's not just that they're low, they're still dropping. And that's very reassuring to see. But this visual explains that very clearly.
Yeah.
Did you do the same thing for Europe?
Yeah, the European stuff we did not so much at the county level. I think if we go to
The states
and provinces, if we go across to well, I guess they're all. If we go to say the United Kingdom, we've got county. We have county level data in the UK, right, Neil?
Yeah, it's their counties are more like our states. They didn't have the granular level. This more like they call them counties, but they're more like provinces and states. And it doesn't do a heat map on that because the geographic areas are so large that it would be a little blocky. But we could certainly add that if we wanted to.
Right, and you still got the velocities down here. The other thing we do that is an example of running an R or Python script is when you get down to look at the reproduction number of the virus. If I go into, say, looking at this by country, and I look at Europe, you can see that there's still some countries that have a reproduction number bigger than 1, which is that's the danger zone. And you see in the visual down here, the green zone with a reproduction number versus time of less than 1. And then some countries like Isle of Man has got a bit of a problem. I mean, Hong Kong at the moment is really crazy what's going on in Hong Kong. Case fatality rate of 5%. But we put in here for this wonderful package, EpiEstim, from the group in the UK, the Imperial College group. You can change the serial interval of which is the gap between one infection and another, the mean and the standard deviation, and you can go ahead and recalculate that. So in this case, we've set up a function that calls out to that EpiEstim R package, and then in this case it's from a menu versus being a marking on a map. This is probably going to take a little while because there's a bunch of different countries here, but yeah, that's the idea.
And it takes like 45 seconds or so on this one. But what I really liked on the previous provinces that you were showing was in the UK, we saw like each of those areas where each of those territories were yellow. So the UK is low in COVID cases, but it's relatively flat. Whereas in the US, we're still seeing a drop happening. And so I wanted to highlight that on the previous chart, but
Right.
Yeah.
But yeah, this ability to be able to run, an R script or a Python script off of a map or off of, and then this has also got a little bit of natural language here. So when we kind of highlight these things, we're saying, what are the most infectious continents? We generate some language to give the lay person a feel for, where the action is in the data. Yeah, I guess it didn't make much difference in the end. We ran that, and I didn't change those parameters very much, really. I just moved the mean up a little bit, and I didn't touch the standard deviation. But yeah, I think that's, I guess, to long-winded answer to Cameron's question, is that I do appreciate having, and this is the GAMLess package. I know the authors of that package. That's a really, really good package for doing nearcasting, so short-term forecasting, and the EpiEstim package here, the mobility, the hotspot stuff, the growth trajectories, and then here's that example that we showed in slides where you can basically pick your, in New York City. I guess we've got a New York City audience here. So if you lived sort of, say, Upper East Side, if I go up there, and I copy those map coordinates and I paste them in over here. And I put a drive distance of, say, 3 miles or so, find the nearby resources to that point. I hope I clicked, oh yeah, I did. I clicked on the Upper East Side there. So those are the locations there. And then, we've got some partnerships. This is Definitive Healthcare is giving us the data for the individual, hospitals and stuff. So, but yeah, this has been a labor of love for me and Neil over the last couple of years. When COVID kind of came out, in early 2020, we started building this thing, and And then we've just been, adding data to it every day at as smaller granularity as we can kind of get. We're getting data from Our World in Data, Johns Hopkins, and a bunch of different states and countries where we've been scraping our own data. So some of the examples that you saw today, we spent a lot of time on these color schemes and everything else that you've seen. So yeah, feel free to play around with that if you've got any suggestions. I know we're kind of hopefully at the end of the pandemic, so maybe we're going to wrap up that example here at some point. But yeah,
just a little plug. So the TIBCO Analytics Forum was mentioned on that last slide. We're going to Ben Schneiderman speaking. Michael and I are going to do some more topics on visual analytics, and it's a free attendance virtual event. So recommend checking that out. analyticsforum.tibco.com. Free event, and there's gonna be lots of different speakers, lots of different analytics. It's a user-based forum where we are trying to make it easier and empowering for different data visualization experts, different data analysts, data workers, data scientists to do their job better and improve on their analytics.
Yeah, and I guess one plug, we got Nadia Bremer as the keynote. So let's see if we got Nadia. I thought I had a screen up for her, but she's got some pretty awesome stuff. She's a JavaScript coder, and we've been adding JavaScript capabilities to our product over the last couple of years, and so she's going to do the keynote, and she's got a lot of interesting examples of visual analytics that she's done for different clients, and yeah, she'll be doing the keynote on day one. So we're excited to have her keynote day one, and Ben keynoting day two. With his, I don't know if you can see that, but that's Ben's latest book. Great.
Are there any other questions? Cameron, was your question answered? I saw you had something in the chat.
I did have something if there's time, but I can also follow up with email if folks have to go. So I'll leave it to Michael and Neil to discuss.
I think I can answer that quickly. I think you were asking what's the design process like in creating these displays, and is it a team or individual? So most of these were all created by an individual. I created many of these myself, and contributions from other data scientists, Peter Shaw and others. But the authoring process is very simple, drag and drop. Drag your visualizations in. You can do custom visualizations in JavaScript if you want, and make those drag and droppable and reusable if you want, or you can use other people's visualizations or the out-of-the-box visualizations. Very easy experience. There's an actual data canvas in there where you can do your data cleanup and data mashup, and there's a inbuilt Python and R engine if you wanted to do advanced scripting and modeling, geospatial statistics, any statistical analysis, all built in right there for you. Yeah.
Yeah, and there's also a question about natural language. Neil, can you take that one too?
The natural language was actually done with partnership with ARIA NLG. So I'd recommend checking them out. They have a really great tool. We also can do natural language as a R data function. It's not as extensive as the ARIA platform, but there is a R script on our community that will generate some basic natural language for you.
Yeah, absolutely. And then for folks who are, JavaScript coders and, know a little bit about Spotfire, there's, you can, there's a bunch of downloads. So if you go to this site here, the TIBCO Exchange, you'll see all these different charts that you can download. And someone has developed these in JavaScript. Either someone at TIBCO or one of our customers has created. Usually based on D3 to begin with, and then you can just when you download them. I've got Spotfire open. I think you can then just bring them in and add them to your flyout. So here's some of the ones that Neil showed today. And then if you want to bring a bump chart, say, into the analysis, just bring it in like that. And then you map, the
Here, yeah. Oh, we lost your audio.
Anyway, idea that,
here, I have it open. I can share real quick if you want.
Okay, yeah, sure. Why would my earbuds take over my voice track when they're tucked away in their little box. I don't know what happened there. Sorry.
So, yeah, so this is just the drag and drop. Like if, you know, I want a donut chart, I can place a donut chart in here. Donut chart, spider chart, gauge plot. You just drag and drop them in. So there's about a dozen or so out of the box visualizations, and then you see about another 20 or so custom visualizations that are operating just like actual custom, or just like actual native visualizations there. So there's the donut chart. I can just actually sector size this by different amounts, and that works just like a native visualization. And then this is the data canvas that I talked about. So you can actually join and link up your data here, add columns, add rows, add transformations. And then if you have scripts in here, like these are R scripts, it'll show you all of your inputs, your R script itself, its outputs, how it maps to your actual data analysis.
Yeah, so we use R scripts extensively for the geospatial part, you know, with great libraries that are in R for spatial analytics. And then we use Python a lot for the machine learning and data preparation. But, you know, there's also, you don't have to use R or Python. There's point and click inside of the product. But we found the R and Python extensions to be pretty popular.
Mm-hmm.
Okay, well, Linda's leaving, so I think we'll leave too. And thank you so much again, Naomi. And I hope we can, hope that some of you are able to come and join us for our conference in June. And I hope we can come join you again for some of your talks in the rest of 2022.
Thank you all for coming. Special thanks to Cameron once again for hosting this, and for his company, the company Datadog, for hosting the meetup. And thank you to Michael and Neil for a lot of food for thought. You covered a lot, and we have a lot to think about now. So thank you to all, and see most of you, I hope, on May 31st, when we'll learn about visualizing metrics.
Thank you, Naomi. Thank you, Cameron.
Thank you, Cameron. Thank you, Naomi. Thank you, everybody. Great to catch up with you, Scott, and everybody else. Bye-bye.